Good day, ladies and gentlemen. I'm Gary Chen, major in AI technology program. Today, it's my honor to have this opportunity to share this topic, performance analysis of distributed file system based on RAID storage for Tapeless storage. Before I start this topic, here are something we have to know first. What are tabs, disk arrays, RAID 6, and their principles? Compare tabs and arrays. Why we choose RAID storage to replace tab storage. Introduce the DFS infrastructure. Through this introduction, it will be easier to understand the content of this article after entering the formal topic. Tab is including tab libraries and tab drives. Tab libraries automate the handling of multiple tabs. They contain multiple tab drives and robotic mechanisms for tab loading and unloading. Tab drives are the primary hardware component of tab storage systems. They read and write data on the mechanic tabs. Tab cartridges are the physical storage media that store data on the tabs. Tab storage functions. A system that uses mechanic tabs as a data storage system, suitable for systems that require large amount of data storage, not only for backup in case of system failure, but also for archiving data for long-term storage, an option for off-site backup. Capacities of tab vary widely, ranging from gigabyte to terabyte per cartridge. Manage the flow of data between the host system and the tab drives. They often include interfaces such as SCSI, SAS, and fiber channel. Over the years, tab has had its attributes, but as technology has evolved, so have its challenges and drawbacks. Weakness of tab: backup speed, recovery time, limited capacity, durability and reliability concerns. RAID, RAID, which stands for Redundant Array of Independent Disks, a technology that combines multiple physical hard drives into a single logical unit to improve performance, redundancy, or both. RAID storage is commonly used to enhance data reliability and increasing input-output performance. RAID levels are used to various environments, including server, SAS storage, NAS storage, and SHIN storage infrastructure. RAID combines multiple hard drives into a logical hard drive, and the OS will only treat it as a physical hard drive. RAID has the different levels for different purposes for set. Show some as the table. There are several RAID levels: RAID 0, 1, 5, 6, 10, 50, 60, each offering different advantage and trade-off for data protection. Each RAID type has different advantage. Some have low cost, some have fast I/O speed, some have the largest capacity, and some have the highest file security. If you choose to advantage according to your need and create a suitable RAID type, but it is impossible to have all four at the same time. RAID 6 is a storage solution that balances performance, cost, data protection, and capacity utilization. Here is RAID 6 configuration with add hard drive disk, include data and parity check. RAID 6 provides two virtual independent parity systems using different algorithms. The reliability of the data is very high. Up to 2 disks in the same array can be damaged. After replacing the new disk, the disk will be recalculated and written to the new disk. In today's era of AI and big data, it is the most common disk array level. This is a comparison table between tape storage and disk storage, focusing on the following 5 characteristics. First, performance. Second, adaptability and viability. Data characteristics. System reliability. The last one is management and administration. After comparing various conditions, we can find that tape storage no longer has any advantages. In all conditions, disk storage takes the lead. In all conditions, disk storage takes the lead. This is why today's data storage is stored in disk storage, and this is why the research architecture is built on disk storage. With its decentralized design, DFS solved various challenges related to data storage, just like the 5 comparisons just mentioned, making it a powerful solution for modern storage needs. Here is a simulation scenario. How can a sales client quickly access files in the DFS system? Here are 7 flows to access DFS system by sales client. First, client request. The sales client wishes to access or operate on a specific folder, such as folder sales or folder financial. Second, request to master server. The sales client sends an access request to the master server of the DFS system. The request includes information about the target folder, as well as the sales client's identity and permissions. Third, authorization by master server. Upon receiving the request, the master server performs permission verification to confirm whenever the sales client has the right to access the target folder. If permissions are correct, the master server determines the slave server responsible for management the target folder sales. The fourth, forwarding to slave server. The master server forwards the access request to the slave server responsible for management the target folder sales. For example, if the sales client requests folder sales, the master server forwards the request to the slave server management folder sales. The fifth, response for slave server. Upon receiving the request, the slave server provides the content of the required folder sales to the master server. The sixth, response to client by master server. The master server forwards to further sales content to the sales client. The seventh, client access data. Based on the further sales content provided by the master server, the sales client performed access to operations. This process ensures that the centralized master server plays a coordinating and controlling role in the entry DFS system. Different staff servers are responsible for managing different folders, archiving, distributing storage, and access performance to data. The DFS architecture just mentioned will be applied to this application of research, and it will look like this architecture diagram. There are 4 servers, 2 types of switches, and RAID storage. The details will be introduced in the following slides. Okay, after introducing this role and elements, now it's the time to share the main topic. Performance analysis of distributed file system based on RAID storage for Tapeless storage. Gary will introduce the background, the purpose, the related works, the production and analysis of experimental results, and then the conclusion. Here is background. In response to the continuous pursuit of performance, this study addresses the changing storage environment by building and evaluating a DFS based on RAID storage. Tape storage has been a traditional choice for long-term data storage due to its initial cost advantages. However, RAID's complexity and higher management cost have diminished its cost effectiveness. Alternatives with lower cost and larger capacities are gaining prominence, prompting a shift away from continuous tape storage investment. DFS employed technology like RAID and ensure coding, present, and compelling alternative. This study evaluated a DFS based on RAID storage, comparing it with Ring-Solomon configurations in the same environment. The technology shift toward Tapeless alternative and the specific focus on this research on RAID storage-based DFS. First, tape storage, traditional use, lower cost, but slow access, complex restoration. Second, trend toward tapeless storage, shift from tape storage, fast, reliable, scalable, alternative. Third, advantage of RAID storage, parallel access, improved performance, cost-effective use of existing RAID infrastructure. Fourth, DFS, replace tape with cost-effective disks. Leverage DFS for large-scale data centers. The last, performance evaluation. Evaluate RAID-based system is intensive environment. This is the infrastructure diagram of this research. In this infrastructure, there are 4 servers, include 1 primary server and 3 secondary servers. Each server is equipped with a single CPU, 96 GB RAM, and utilize one hard drive for OS boot with an additional 2 hard disk configurations in a mirror for fault tolerance. Therefore, servers are interconnected through a 10G interface Ethernet switch. The 3 secondary servers are future connected to a RAID storage system via 2 8GB interface using a fiber SAN switch. The RAID storage system is configured with 8 hard drive disks in a RAID 6 setup. The overall system encompasses computationally power with the servers, storage space, and performance. Establish the structure firmware for this environment. Here comes to introduce the infrastructure of EOS and Cluster FS. EOS, Development for Stable Storage Technology, notably used in LHC experiments. Components: MGM for metadata management, FST for storing files, and MQ for asynchronized communication. Create a network RAID storage system with inertial coding support. Provides cost-efficient, reliable, and scalable storage solution. Clustering FS designed for scalable and high availability storage solution in large-scale distributed configurations. Offers a unified namespace for clustering multiple servers over a network. Supports automatic loading balancing and built-in fault tolerance using inertial coding. Suitable for environments like cloud and big data that require scalability, availability, and fault tolerance. Different DFS layouts were used in the experiment. See left table. Cluster FS employed a linear storage approach, utilizing all available space without redundant distributed layout. In contrast, EOS utilized the plain option for replication. Clustering FS used the replication option, while EOS employed replica, allowing data recovery for up to a -1 node value, but reducing storage space. Utilization to 1/n. The RAID 6 RAM layout employed ensuring coding and parity data different between EOS and Cluster FS, offering resilience against up to 2 node value. The right table details configurations for the FIO benchmark tool in performance emulations. The test assesses performance across 8 block size using a 6 GB work size. Measurement were taken for 8 straight entries. Analysis latency and performance under varying workloads. For I/O patterns, read, write, random read, and random write were examined to scrutinize results in each pattern. In summary, both CERN, EOS, and Cluster FS adopt DFS infrastructure, implement replication mechanisms for fault tolerance, and leverage rate-like technology. Ran layout and link Solomon ensure coding to enhance data reliability and availability in different ways. The choice between them would depend on specific requirements and use case. I will talk about that later. The following slides will be comprehensive benchmarking across 3 different DFS layouts, namely read, write, random read, and random write by 3 benchmark types: regex ran, replicated, and distributed. The experimental architecture is shown in these 2 tables. This experiment will provide insight into DFS behavior and its performance impact in real-world scenario. After the 24 experimental scenarios just listed, now let's view and analyze the experimental results. Regex layout read benchmarks. EOS shows increasing bandwidth with workload, while Cluster FS maintains stable performance. Latency spikes after 8 straight, with Cluster FS have higher latency at 64 and 128 straight. This result, EOS is preferable for massive workloads, whereas Cluster FS offering consistent performance. Replication layout read benchmarks. Cluster FS excels with fewer straights. EOS slightly better for 16 to 128 straight items. EOS outperforms Cluster FS, especially a higher straight count with smaller block size. This result, Cluster FS is generally superior for fewer straight, while EOS shines in specific conditions. Distributed layout read benchmarks. Cluster FS outperformed EOS for most items, maintaining a slight advantage. No significant latency difference observed. This result, Cluster FS demonstrates an overall performance edge in distributed read items. Regex ran layout write benchmarks. Cluster FS showed consistent performance. EOS throughput increasing with straight count. EOS outperforms Cluster FS for large straight counts and small block size workloads. This result, EOS is superior for extensive workloads, while Cluster FS excels in other scenarios. Replication layout write benchmark. Cluster FS experiences LPS drop and bandwidth degradation, indicating workload impact. EOS exhibits consistent performance but higher latency than Cluster FS. This result, Cluster FS is more stable for write operations. Distributed layout, right benchmarks. Cluster FS maintains consistent performance. EOS throughput increased with thread count. EOS performs better at high thread counts and small block size workloads. This result, EOS is suitable for substantial workloads. Cluster FS for optimal performance at low thread count. RAID 6 Run Layout Random Read Benchmark. EOS saturated at 8 threads with decreasing bandwidth and increased latency. Cluster FS exhibits high bandwidth at 1 thread, showing better overall performance. This result, Cluster FS is a superior choice for random read. Replication layout, random read benchmark. EOS throughput drop after 4 threads. Significant latency at high thread count. Clustering FS generally outperforms EOS for all threads. This result, Cluster FS is preferable for random read. Distributed layout random read benchmark. EOS throughput peaks at 16 threads, then sparkly decrease at 32 threads. Cluster FS exhibit variable throughput but maintains stably. This result, Cluster FS provides stable throughput. RAID 6 Run Layout Random Write Benchmark. EOS shows consistent throughput increase. Cluster FS exhibit higher initial performance. Cluster FS has higher latency and low performance at high thread count. This result, EOS is advantageous for large workloads. Cluster FS performs better at low thread count. Replication layout random write benchmark. EOS shows minimal throughput variation. Cluster FS generally perform better. EOS exhibits higher latency at 128 threads. This result, Cluster FS offering better overall performance. Distributed layout random write benchmarks. Cluster FS throughput increases up to 4 threads, then sparkly decrease. EOS maintains consistent performance from 2 threads onwards. This result, EOS is more consistent. Cluster FS performs better at low thread count. Here is the conclusion. This conclusion summarizes the key findings for the performance analysis study. First, significant performance differences. Despite identical hardware environments and methods, a notable performance gap existing between the two DFS. Thus, choosing the appropriate DFS execution based on the specific situation. Second, variability in bandwidth, IOPS, and latency. Factors like layout, thread load, and block size contribute to substantial variations in bandwidth, IOPS, and latency. Understanding workload characteristics is vital to predicting and managing performance outcomes. Third, DFS selection in RAID storage. In RAID storage setup, EOS is favored for substantial workloads, while cluster-FS ensures relatively consistent performance across varying workloads, particularly for random tasks. The fourth, configuration insights. This research configure and compare DFS with RAID storage, emphasizing the need for a nuanced understanding of workload characteristics. The approach offers value insight into a performance nuances of RAID storage-based DFS suitable for Tapeless storage. The last, varied performance based on workload nature. This research finding underscore the substantial performance variability of DFS based on workload characteristics. Tailoring solution to specific cases is crucial for optimal performance outcomes. This is a reference. Thanks. I'm Gary Chen. I hope this research was informative to you. Wish you a good health and safety. Goodbye.